that's on the internet. And this is where we show you grade keeping results and that kind of stuff. Here's what you'll find in the CLC schedule. Actually, you gotta put it there. I haven't put it there yet. It'll be there this afternoon. And all information like this, when I post it, is under resources. That's where you'll find past quizzes, exams, bonus quizzes, solutions worked out, all kinds of stuff for you to practice on to your intellectual heart's content. All for your benefit. Now, last time, you don't make two mixtures of identical composition. Iodine, toluene, water, potassium iodide dissolved in the water. After we assemble these systems without any agitation, this is what we have. The toluene phases are on the top in each case. In cylinder A, we started with all the toluene, with all the iodine dissolved in the toluene phase. And you can see from observation that principal quantity of iodine is still in the top toluene phase, which is less dense in the lower water phase. But you can see a little bit of yellow coloration in the lower water phase, showing that on passing of time, some of the I2 migrated from the top phase into the bottom phase. Is it also true that while some of the iodine has been migrating from the top phase to the bottom phase, that it's also migrating from the bottom phase back to the top phase? This is a dynamic system. The particles contained within have translational motion. Now, in cylinder B, we started with all the I2 dissolved initially in the water phase. And as we recognized last time, since toluene is at best slightly polar, and I2 is not polar, the I2 is principally soluble in toluene, or much more soluble in toluene than it is in water. So on standing, we've seen a fair amount of I2 migrate from the lower water phase, which initially contained all the dissolved I2, into the upper toluene phase. But again, since these two systems are compositionally and quantity identical, we can recognize they're not in equilibrium because if they were, they'd look alike. And as things stand, which we talked about last time, which is discussed in the notes, the only way I2 can migrate from top to bottom or bottom to top is through this interface. So in order to increase the rate at which I2 transfers between the two phases, what we really want to do, at least the simplest thing to do, is to magnify considerably the area of the interface. And we do that by shaking. So I'll do a little exercise. And agitate each cylinder thoroughly. Here's now that we're getting into equilibrium, because now the contents of each flask are quite the same. So let's tackle a consideration with respect to this system. Quantitative investigations solubility of I2 distributed between toluene and water is a value of about 70.0. In other words, I2 is 70 times more soluble in toluene than it is in water if studied at normal laboratory conditions. So if we speculate that 0.500 grams of I2 has been dissolved totally, we wish to ask the question, based on this distribution equilibrium constant, can we calculate the mass of I2 in each liquid phase at equilibrium? Now, for the case which we demonstrated, the system volumes are equal. But we're going to jump to question 17.9, where we have considered a mixture of of water and toluene in this volume ratio, or volume quantity. 900 milliliters of water, 100 milliliters of toluene. Notice that here we have 200 milliliters of each liquid. Here, 9 times the volume of water compared to that of toluene. In this mixture, where we've dissolved the I2 in a liquid system, which is volumetrically in favor of water by a ratio of 9 to 1. Will most of the I2 dissolve in water for that system?
No, because since it's 70, it's only 9 times more the water compared to the toluene, so it's not enough.
Tell me, if we're going to make a mixture of water and toluene, and this is the distribution equilibrium constant, how must the volume ratio of water to toluene compare to this number? If in equilibrium, most of the I2 will dissolve in the water layer. What must the volume ratio be? Greater than 70. Then most of the I2 will wind up in the water layer. And not until we have a volume ratio of water to toluene, which is greater than 70, will that be achieved. Now, before we proceed with this arithmetic, did you perchance in 2045 consider the structure of this molecule? What's the name of this molecule? Carbon tetrachloride. You know, I don't consider it to be all that important in first-year chemistry that we know names of formulas, so long as we have the formula itself. The formula itself conveys to us what we need, much more so than the name. But in this case, again, based on rules of nomenclature, you likely learned in 2045 that's called carbon tetrachloride. The shape of this carbon tetrachloride molecule. Tetrahedral, is it polar? If we made, if we did this experiment using carbon tetrachloride instead of toluene, how would the distribution equilibrium constant compare to 70? Would it be bigger than 70?
Yes.
Why? Because carbon tetrachloride is not polar whatsoever. That's right. In fact, studies show that the distribution equilibrium constant for carbon tet water with I2 as the solute is 80 to 1. All right, back to this arithmetic. As a ratio of molar concentrations of I2 volume to I2 in water, as we've already noted, the distribution equilibrium constant is 7.70.0. So if we have dissolved 0.500 grams of I2 total, what can we do to calculate the mass of I2 in each liquid phase after we've established equilibrium? Well, notice that the quantity of I2 is expressed in grams. And this equilibrium constant is a molar concentration ratio. So in order to, you learned this in 2045, when for a substance, any pure substance, you have to go from moles to mass or mass to moles, what property of the substance always allows you to make this connection? Called formula mass or molar mass. Doesn't matter, these terms are equivalent. The most common, I think the most common symbol used for molar mass in textbooks is this rather fancy M, or something like that. You seen this for molar mass? Well, I'm not all that adept at making this scrawl, so I just use FM for formula mass. But this is the same as this, as written by me. So I've taken the liberty of expressing the inverted formula mass for I2 in the numerator as well as the denominator of this concentration ratio. Because this is the ratio of molar concentrations, so I need moles of I2, toluene, pardon me, divided by moles of I2 in water. So that's what I've written. Do we need the numbers? Let's see if we need the numbers. If I have the inverted molar mass, formula mass, which is moles per formula mass expressed in what unit? Grams, okay? I have moles per gram for I2, numerator, denominator. What do I have to multiply by? What do I have to multiply this inverted formula mass by over here to get this? Now, before we go further with that, if I represent the mass of I2 that's at equilibrium in the water layer as X, how will I represent the mass of I2 at equilibrium in the toluene layer? Do I write down Y? You realize if I write down Y, I'm going to have two unknowns. I only got one equation. If I've got two unknowns contained in one equation, can I solve it? I know how to do that. What should I write down? Algebraically, how should I represent the mass of I2 in the toluene phase if X is representing the mass of I2 in the water phase?
25 minus X.
I should write this. Now I have only one unknown. So what am I going to do? Well, unit analysis tells me. We can do any problem in science class where the quantities that you are considering always have units. You always want to pay attention to units. You always have to do dimensional analysis. Or if you prefer more simply called unit analysis. Moles of I2 dissolved per liter volume of solution. So I got moles of I2 per mass. Up here is toluene. What do I write here? Remember, this is the system I'm considering. Let's get this out of the way. What do I put here? For this system, what is the volume of toluene phase? Will you accept this? Instead of 100 milliliters, I'll write 0.10 liters. So, over here, or in the denominator for water, I'll write this. And now, recognize we don't even have to pay attention to the numerical value for the formula mass or inverted formula mass for IT. Don't do any arithmetic that you don't have to do. So I got one equation, one unknown. Solve it. If you solve it correctly, you should get 0.057 grams. And of course, 0.500 grams less 0.057 grams to give the mass of I2 that's dissolved in powder. Now we proceed. Quantitative analysis of equilibrium systems. With what you folks have done earlier this week, you know how to write equilibrium constant expressions. You recognize they can always be written for the equation for the equilibrium reaction. So I trust you realize if you are going to tackle an equilibrium problem that involves a reaction, and just about all equilibrium problems will involve a chemical reaction, what should you do first? You're going to tackle an equilibrium problem that involves a reaction. What should you do first? Write the equation for the reaction. That's right. Because with the equation for the reaction, you can write the equilibrium constant. And then you have the tools or the information necessary to go further with analysis of the problem. So I'm going to tackle a problem which you'll see worked out in detail in the notes. But as I do this conversation, I will ask that you don't look at the notes. Instead, pay attention to what we have on the board and think through this. Because the intention of this is to see to it that you know how to push these equilibrium. On page 1717, the notes tell you about making a mixture. This is my shorthand reference to consider. Of 0.200 moles of nitrogen and 0.300 moles of hydrogen in a 1.00 liter flask. Have you recognized, or did you learn this in 2045, that if I pay attention to a system that has a volume of 1.00 liters, that concentration for system components are numerically equal to mole amounts? And one thing I like to do is when we begin to tackle these problems, keep the arithmetic as simple as possible so that we can digest the chemistry. Because once you got the chemistry, you can always do the arithmetic. Now in this case, since a whole bunch of equilibrium problems which we're going to tackle in the future will involve solutions, water solutions, where we have to pay attention to equilibrium constants expressed in terms of concentrations, specifically molar concentrations like this one, we're going to tackle this one as a concentration analysis. So case of C, where C means concentration, as opposed to case of P, where P means partial pressure. You've already talked about that earlier this week. If I tell you that in this 1.00 liter flask, we started with a mixture of this much nitrogen with this much hydrogen and no ammonia initially. And we observe by measurement, after equilibrium is established, we wind up with a molar concentration of nitrogen of 0.190. Calculate Kc. So here I have gone ahead with writing the equation for this equilibrium reaction. I expect that you've seen this equilibrium reaction previously. Again, since we have the equation, we can write the equilibrium constant expression. We could write this equilibrium constant expression as a Kp, or in this case Kc, because again, we said we want to consider this as an analysis based on concentration. Here are the initial quantities. We said that the equilibrium concentration for nitrogen is this, which will be the same as the mole quantity, because it's a 1.0 liter volume system. Now, to go from this to this, we experienced a change, didn't we? So we could write in here C or delta, because we often use delta to refer to change. So, for those of you who've seen this stuff in textbooks, initial, change, and equilibrium. The textbooks very often call this an ice state. And students oftentimes come to me after we've done an analysis like this, and they say, why don't you use an ice state? And I often say, well, what the hell do you think this is? It's an ice state. If I started with 0.200 moles of nitrogen and wound up with 0.190 moles of nitrogen, how much ammonia did I make? Statement. The most common difficulty that students like yourself have in doing equilibrium problems successfully is not paying attention to stoichiometry. What do I mean by stoichiometry? For this system, what defines the stoichiometry? What do we have on the board that defines stoichiometry for this system? What is it? The reaction equation. A reaction equation is oftentimes a stoichiometric relationship. Because in 2045, you should have learned that a reaction equation, or equation for reaction if you prefer, is a recipe. It's not a guarantee of outcome. It's not a promissory note. It never tells you how much you have. When I do 2045, I will write an equation like this on the board. And the first thing I will say after I write the equation to my 2045 students is, tell me what this means. And invariably, a student will say, it means you have 1 mole of nitrogen. And I say, where the hell is it? Show me. Well, of course, if you think about it, there's a whole lot more than 1 mole of nitrogen in this atmosphere. Oh, by that logic, it will also mean I have 3 moles of hydrogen. You think there's 3 moles of hydrogen in here? You think there's any hydrogen in here? How about ammonia? You think there's ammonia floating around in this atmosphere? Are you familiar with the odor of ammonia? Is it a pleasant odor? Is it like roses? Would you like to take a cap off a bottle of household ammonia that's often used for cleaning purposes in the home, remove the cap and go, I don't think you want to do that. So I'll go, I don't pick up any ammonia odor in here. The equation for reaction doesn't have anything to do with how much I have. It's a recipe. It's an if-then clause. And that's why it's a stoichiometric relationship. As written, this statement says, if 1 mole of nitrogen gas combines chemically with 3 moles of hydrogen gas, then I will make 2 moles of ammonia gas. But it tells me nothing about conditions, and it tells me nothing about how much of these starting materials I may or may not have, and it tells me nothing about whether or not there's any of this in the system initially. Nothing. The only way you can find that out is by measurement, or by somebody telling you. So, back to this. How much ammonia have I produced by this reaction if this change occurred 0.200 moles to 0.190 moles as equilibrium was established? Will you take that? Because this statement tells me, if I use a mole of this, I can make 2 moles of this. How much of this did I use? 0.010 moles. So I will have made 0.020 moles of this. So how much of this did I use? How much of this did I use? 0.030. Don't forget the significant figures. So how much of this do I have in equilibrium? 0.270 moles. And now I can put the information in and do the calculation that I was asked to do. And when I grind this out, what do I get? We've done the important part. I get 0.1. Now that's another question. Is this the same system as this?
Yes.
Is this exactly the same system as this? Yes or no? Because if this is exactly the same system as this, and I don't change temperature, then I'm going to have the same equilibrium constant for that reaction. Does this reaction, this equilibrium reaction at the bottom, have the same equilibrium constant? No, it doesn't. It's got ammonia to the 4th power in the numerator, and nitrogen molarity squared in the denominator, and hydrogen molarity to the 6th power in the denominator. So I ask this question. If I consider this system at the same temperature and pressure as this system, what is the value for Kc?
0.121.
What is it?
0.121. We're not taking any figures. Oh, 0.01.
I'll ask another question. Is the value for Kc for this equilibrium reaction larger or smaller than 0.1? Larger or smaller? Smaller. Because in order to convert this equilibrium constant and this equilibrium constant expression to this equilibrium constant and this equilibrium constant expression, what do I have to do with this equilibrium constant expression? Square it. That means I got to square Kc. And whenever I take a number that's smaller than 1 and multiply by itself, I'm taking a fraction of a fraction. That means I got to get a number smaller than the number with which I began. I think this is right. Let me take a look. Yeah. Can I legitimately express this equilibrium constant to any greater number of significant figures? No. Only got 2 there. And this calculation was based on that. I can only report 2 here. Another equilibrium reaction. This is also discussed in the notes. And for this equilibrium reaction, we want to take a look at question 17.4. You don't have to read back through the notes to find question 17.4. You'll find it as it's contained in the discussion section where this equilibrium reaction is discussed. This equilibrium reaction is discussed along with conversation that involves a relationship for a gas phase equilibrium, like one we just considered. Whereby we are choosing to interconvert the Kc value to the corresponding Kp value at the same temperature. That's not going to be a real concern to us when we get to chapter 21. So I'm not going to bother with that issue extensively at this point. But I will ask this question. For this equilibrium reaction, if we study this equilibrium reaction at a temperature and pressure at which the behavior, or for which the behavior of water in the vapor phase is describable by this relationship. You've all seen this relationship. What does it mean? One way to talk about that relationship is to call it an equation of state. Have you heard that? What's that mean? Equation of state. Were you told in 2045, when you read through the conversation in the textbook, and the textbook writes that relationship and calls it an equation of state? If the textbook at that point doesn't tell you what an equation of state itself is, and you don't know what equation of state is, what should you do? Find out what the hell equation of state means before you proceed. Otherwise, what you're reading doesn't mean anything to you. Equation of state, because this relationship, provided these gases exhibit a behavior that is called ideal, this will describe properties of a system of these gases because they are behaving ideally in terms of pressure, volume, moles contained, and temperature, expressed in terms. So if this stuff is behaving ideally as a gas component of this system, is it true that this stuff will behave ideally? This stuff? This stuff? Will the other gas components of the system behave ideally and have their behaviors describable directly by this relationship, if this relationship holds to the behavior of water vapor? Did you study stuff like this in 2045? You're damn right you did. But it may not have been phrased as I have just phrased it. When does a gas behave ideally? Under what conditions does a gas behave ideally? In order for a gas to behave ideally, have its behavior describable by T equals nRT. What properties of the system of gases, what properties must be exhibited by this system? Intermolecular forces must be negligible. What else? We have to have a system which is of sufficiently large volume that the volume occupied by the molecules themselves means nothing. And we have to have a system where the measurable, observable tendency of the molecules to stick to each other means nothing. Then we got a system that's ideal. No system is perfectly ideal. Because every molecule, every atom exhibits at the minimum what kinds of interparticle attraction forces? Dispersion or London, call it either way. But if this stuff, water, shows a behavior at a particular temperature and pressure, which is describable by this relationship, will this relationship also serve the purpose of describing the behavior of CO, CO2, and H2? And the answer is, you're damn right. Now, why is that the answer? What do you know about water molecules and their tendencies to interact with each other, associate with each other? They're hydrogen bonders, aren't they? Not only are they polar, they're hydrogen bonders. If I take this system in the gas phase, and I begin to cool this system, which of these molecules will first liquefy? Water, because its intermolecular attraction forces are the strongest. So if this damn thing is behaving ideally, you can bet the other particles are behaving ideally. Right? Because the interparticle attraction forces among and between water molecules are far and away the strongest. After all, under normal laboratory conditions, water is a liquid with a fairly high boiling point. How about these other material components of this system? at normal laboratory conditions. Are they liquids? Are they solids? No. Now, question 1711 is applied to this system, but since we told you this relationship holds for this system, you can do the arithmetic to calculate the temperature asked for, question 1711. Let's go to 1719, page 1719. I've written for you a directive. Here's the directive. There are only two different molecules involved in this equilibrium reaction. Nitrogen dioxide in equilibrium with dinitrogen tetroxide. This reaction read left to right, as I've written it. It's called a dimerization reaction. You heard that term? Dimerization. It means that if this goes left to right, how many of these molecules get together to make one of these? How many? Two. So they dimerize. On with this test. Right now, let's go. Structure, the most important property of any species. We want structure analysis for these right now. When you are going to make a Lewis structure, what is the first property of the species that you pay attention to? The number of valence electrons. How many did you come up for NO2? 17. It's an odd electron molecule. Therefore, it is known as a radical. Did you hear that term, 2025? I brought your attention to that term in the discussion section for 45 laboratory assignment sheets, which gives you a detailed discussion of how to make Lewis structures, all of which is condensed in chapter 23 of these notes. I've already told you, if you need review on making Lewis structure, you got it, it's in the notes. So I offered you two Lewis structures for NO2. Notice that in this Lewis structure, for non-bonding electron pairs, I also used this stick. I'm up here working in a dust storm of chalk. I don't use dots for single electrons, unpaired electrons, unless I have one. I mean, I don't use dots for non-bonding electrons unless I have a half-filled orbital, like this NO2 radical. How many of you wrote at least one of these Lewis figures? Which of these Lewis pictures for NO2 do you like better? When you have written a Lewis structure, what device do you use to constructively criticize the Lewis structure? Formal charge. If you do formal charge analysis on this, you'll get +1 on the nitrogen and minus on this singly bonded oxygen. But for this Lewis structure, you'll get 0 formal charge distribution throughout. So based on formal charge distribution, this is the preferable Lewis structure. But when I asked the question, which of these Lewis structures do you prefer? The only response I heard, although it was rather faint, was for A. And that's correct. Why? Now, we do see for A that the minus formal charges on oxygen, which is the more electronegative atom than nitrogen, so that part's okay. But why is this Lewis structure preferable to this Lewis structure, even though this Lewis structure shows zero formal charge distribution?
Nitrogen has 7 valence electrons, while oxygen has 8.
Which is the atom of greater electronegativity, and therefore has by far the stronger tendency to fulfill its octet requirement. Which one? Nitrogen. Oxygen. Which one? Oxygen. So for A, we have the oxygen each in an octet environment. That means, if this analysis is correct, when NO2 molecules react with each other to make an N2O4 molecule, would you be surprised to find that in this reaction the only bond you make is an NN bond? Because all the nitrogen atoms for each NO2 molecule bump into each other, and these unpaired electrons on the nitrogen atoms partner up and become a shared electron pair, a covalent bond, which tells you immediately how to write the Lewis structure for N2O4, because it has an NN bond. It has no OO bond, nor does it involve forming another NO bond. Strictly an NN bond is formed. Did you also learn that radicals have a tendency to electronically interact with light in the visible region of the spectrum? And materials which interact with electromagnetic radiation in the visible region of the spectrum exhibit what property? What's it called? Simpler term. Clear! How about that? Yeah! So I'm going to show you a flask. See this flask? And I'm going to tell you that this flash shows its brown coloration because it's got NO2 in it. And it's also got N2O4 in it, which is colorless. Because since this reaction is gas-phase and therefore dynamic, any NO2 N2O4 mixture at whatever temperature and pressure such a study will be an equilibrium mixture. And here I have an equilibrium between NO2 and N2O4. We're going to analyze this system in detail when we get to chapter 21. But I want to go back to the question that I was applying to ask all along for this system, and that is this reaction guaranteed endo? Is it guaranteed exo? Or is it the case that I don't have enough information to tell? Three possibilities. You have to vote. If you don't vote, before you leave, I get from you $100 and we're having pizza and beer on you. Guaranteed endo. Guaranteed exo. Can't tell. Most votes were correct. Flatly and absolutely guaranteed exo. Because the principal character of an exo reaction is what? Bond formation, or bond strength increase, or both. Bond improvement. And this thing is strictly a bond-forming reaction. Now I'll ask you one more question, and we'll talk about this at the start of our next gathering. And then we're going to proceed with challenge problem 17.1. Take a look at it. What can you say about the bond angle for the NO2 molecule? Value for the bond angle. What can you say about it? Pick it up in this white next time.